Again, welcome everybody. Today we are covering data review. So part 3 of our series on ARM and statistics. The first one we just gave an overview of kind of the whole gamut of the at least the simple statistics that most often are done with trials that are put into ARM. Then earlier this week, we did data confirmation, talking about the process and the tools for once you've put the data in, just making sure that the data that's been entered is accurate. Now, kind of the next step, once we have that accuracy, ideally, we'd love to just dive into the analysis. That's kind of going to be our starting point here. I'm going to review real quickly over a couple of those slides from day one. We'd love to dive into the analysis. And as we talked about in the first day, we're really doing an analysis of variance. That's how spread out the data is. We're going to break apart what we see, all of those observations. We're going to do our best to break them up into, break the variation into what we know, the blocking structure, the treatments. That's all of our controlled effects there, and then everything we really can't get our hands wrapped around, don't really know for sure what this is. That is your uncontrolled or your experimental error. So in general, we're just thinking about the response that we saw, the data we've collected. There's your overall, your baseline response, like as if nothing would have happened in the trial. Then you have those controlled effects from the treatments and the blocking that we purposefully went out and did in the trial. And then you've got those random effects that we couldn't control as well. And so if we want to perform that analysis and draw conclusions about those controlled effects, the treatment effects is what we're most interested in. We really have to kind of get a grip a little bit on those uncontrolled effects. And so the trick is that we're going to have to make some assumptions about what those are like in order to be successful in our analysis. And so that ends up being today's focus here, is on those assumptions of AOV. And we covered these in great detail in our first session, so I won't go through each one, but we talked about the different assumptions, and at least the first two, the homogeneity of variance and the normal distribution, those two we have some statistical tests that we can run. That'll give us a pretty nice cut and dried answer. Hey, is this a concern or not? And we'll go through those tools today in ARM to actually do that. Let's test against these assumptions. If everything is good, we have a good evidence that none of these are a problem, then we have a green light to the analysis. Everything's great. Now we're ready to go and report. Of course, we're not always that lucky. And so we talked about some of these options that are available to us if those assumptions are not met. And again, we've got kind of really one tool in ARM that'll do all of the testing for us. And then it'll also help us with this step as well. If those tests come back with something wrong, something we have to do, let's dig into this toolbox between our transformations or some spatial models or non-parametric statistics. We've got a bunch of options for things we can do to adjust the data or adjust our analysis so that once we're ready to actually perform that analysis, everything will work out great. All right, so that's enough theory for us today. Let's dive in here to ARM. I've got a trial open. There's a variety of assessments here. Some of them kind of rigged up a little bit to see what we're hoping to see, I guess. Various examples of things that you might run into. So from the assessment editor, really the main tool for this data review process is Column Diagnostics. So over here on the right, you may see the properties panel by default that comes up, or you might have it hidden by default. We used that a bit last time around for like the assessment map and our box whisker. Today, we don't need the regular properties panel. So you can either unpin that. For me, it's already unpinned, so it'll just go away if I click that. There we go. But all the way to the right, there's a couple of other panels that are available to us. And I want this one that says Column Diagnostics. So that'll pop open for me. You can resize it so that way we can see enough information. I don't have tons of space here for my screen, so I'll try to just move these panels a little bit and move them back once we move to the next pane. But what we have is a bunch of information just depending on which column your cursor is in. So you'll see as I switch between column 1 and column 2, this information on the right is all changing. So the focus here, of course, I'll just start with column 1. You can also see that at the very top, if you're not quite sure which one it's calculating from. So there's a couple of different sections on this tool. The very first one here at the top called Diagnostics. And this is primarily a large table with a bunch of descriptive statistics about our data. Again, specifically column number 1. So we have things like the number of data points. There's 24 data points here. How many are unique values? So you can tell there's a fair number of repeats. They're all kind of hovering between 60s and 70s. So not surprising there's not as many unique values. Then we have some indications of any missing or excluded data. So of those 24 data points, all 24 are being analyzed. If we had, if we had to throw out a replicate or a particular treatment number or a single data point, those would begin to show up here on whether we've excluded them or just accidentally didn't enter a value in there, things like that. And since we have all of our data points, we've got, of course, 4 values in every replicate. So that just gives us, like I said, an overall view of the data a little bit here, just what we're looking at. Moving down the table, though, we do have some statistical tests. You recognize some of those from our discussion previously. These are our tools for testing against those AOV assumptions. So the Levene's is going to test for homogeneity of variance. And then the next 3, Shapiro-Wilks, skewness, and kurtosis, they all tackle various aspects of normality and how bell-shaped our distribution would be. What we have in the table for these statistical tests, we are reporting the p-value from the test. And really that p-value then is a probability of each individual test, the Levene's, being the homogeneity of variance, etc. So if you have a small enough value, if the value is small enough that it's significant, so lower than your alpha level of 5% typically, if the reported value is below that, that's an indication we have an issue. That's an indication that the test is failing and there is some sort of action that we'll need to do. And then each of these columns in the table will be a different potential action we can take. So right now we have just two columns. There's the raw data, and then the second column for IID, that stands for identically and independently distributed. In this situation here, that column is really referring to running these tests on the residuals of the data. Whereas this first column, we're running the tests on the raw data points themselves. So as far as which one to use, which one are we looking at to decide what's important, the kind of the modern statistical approach is to use this second column, really testing the residuals, really are the idea of the error behind the scenes, and we're wanting to test if those errors are, homogeneous, if the errors are skewed or kurtotic, things like that. So that's really where we want to look at all four of those. Are any of them significant? Well, in this case, they are not. So we have really no issues whatsoever that we would need to worry about. Everything's great here. No action is needed to be taken for this first column. So we could just move on to the next column and do the analysis. What we do recommend is actually using this IID action code. So it's in addition to this heading, being our reference here, it's also an action code. And if I click the little checkbox here, you'll see in this column 1 that action code was put into this column. Now, normally an action code is going to do something or tell ARM to do something later on. In this case, the IID technically does nothing. It's not going to change the analysis in any way, but it's a way for us to just mark down that, hey, I've reviewed the assumptions of ANOVA and there just wasn't any action for me to take. So by putting in that action code, that's a nice indication that, hey, this column has been reviewed. So later, if someone else opens the trial, or even if I open it another week later and I've forgotten what I've done in what trial, I'll be able to see very clearly, oh, data review has already happened here. At least for this assessment, maybe I've added new assessments I need to go ahead and review before I go to print off my report. So that's kind of the second use. A couple of different places this IID shows up, but it's just nice simple way just to have a little check mark of, yep, this has been reviewed, but no action is necessary, and make that clear to everyone. Because if we just have an action code blank, there's no place to mark that down. It's maybe not super obvious whether we've reviewed it or not. Okay, moving on to column number 2. You'll see just moving to that next column, all of a sudden, we have a little bit more going on here. You can see some shading here. So just to help us pick things out so you're not just looking at a whole bunch of numbers and getting dizzy or overwhelmed, we do shade in with kind of that required color, that pink required color here on the screen whenever the statistical test, that p-value, is indeed significant. So we can see that Levine's here under the IID has triggered 0.02 is lower than our alpha, giving us an indication that maybe this data is not as homogeneous as we'd like it to be. So that's going to trigger some ideas for us. We do need to figure out something to do here, because if we just ignore that problem and run the ANOVA, our results might mean nothing at all. We really need to fix this assumption in order to be able to proceed with our analysis. So ARM has a couple of action codes here. There's an AL, which would be your log transformation. There's a square root transformation. And then AR is our rank transformation, which is really just non-parametric statistics, but we'll cover that in a little bit. What I can do visually here is look across to see what happens in a couple of these other cases. We fix the Levine's test. If we were to apply a log transformation to this raw data, then when we run the Levine's statistical test on that transform data, we end up not having an issue. So like we talked about in that previous session, the idea of this transformation isn't that we're changing the results to fit what we want. We're applying the same mathematical formula to every single data point. So we're not changing the results as how they relate to each other. We're just changing the underlying distribution of the data so that hopefully that distribution fits these assumptions that we're talking about. Because if it does, then we can run that data through our ANOVA and draw some conclusions. So that's the idea with the logarithm, with the square root. That's what we're doing. So we're happy with either one of these does fix the Levine's. But I do notice, just looking around, if we do the log transform, we do pick up another problem. So although we fix the Levine's, now we've got some normality issues that Shapiro-Wilks just gets underneath that 0.05 to say, hey, there maybe is a concern here that after doing the log transform, our data is maybe not quite as bell-shaped as we would like it to be anymore. Square root, though, doesn't have that problem, and I can see actually all four of these pass under the square root. So maybe the square root is the way to go. However, we don't really have to spend that much time just staring at this block of numbers. Might get a little old depending on how many assessments you're performing. I'm going to drag up this second portion of our panel, the recommendations tab here. So what this aims to do, maybe I'll bring it down just a little bit so we can reference this table above. The recommendations table starts out where we always want to start out, looking at the results of this IID for those 4 tests. And that is what we have in this table, the results of those 4 tests that we run. And the recommendations, ARM looks to see what passes, what fails, and gives us a recommended action to perform. So if I look under the Shapiro-Wilk, if you remember, that one is not significant. And so there's a comment here, it does not fail that test. So IID would be all you would need for this test. No action at all. Of course, for our Levine's, that's our focus here. We do fail that Levine's, and so there's a recommendation to transform that to stabilize the variance. So there's just a little algorithm ARM can run to do what I just described with this table, but much faster. I don't have to sit and look at all these numbers and get dizzy staring at that table over and over again. We can do it all in a second, have ARM do it, and calculate that for us. And we arrive at the same idea of the AL. Now we do actually have a an added benefit here on the recommendations as well. This basis option allows us to give a little more information to ARM as it tries to come up with a recommendation for us. So this drop down here, there's really 4 pieces of information, things we can have ARM look at as it considers the list of options for what to do if one of these tests fails. By default, we're set to the assessment values. So that's kind of not looking at anything other than just the data points themselves. We're really just kind of looking like what we did at this table here, just running the test on with each of the transformations and seeing what happens. But I could point ARM to the action codes field, or the rating type, or the rating unit, so that ARM knows what type of data this is. So if I click on rating type in my column number 2 here, we see that this assessment is a disease count. And there's a column here in this list called family that the algorithm here in the recommendations uses. So this is the way ARM knows what type of data we're working with. This is actually count data. And now that I've changed the count to be count data, you'll notice that the recommendation is actually different now. Now we've arrived at the square root transformation instead. So ARM has that knowledge of which transformation is commonly used with which type of data. We kind of ran through those in our presentation in session 1, so I won't go through each combination again. But in this case here, we really tossed out the logarithm transformation because that never really works well with count data. But the square root, that one oftentimes does. So this is kind of a way using that basis to smarten up ARM in this recommendations engine to get the best option possible. And you could do the same thing with the rating unit. It's the same idea. So depending on your assessment or how you've described it, one or the other might tell ARM a little more about the information. You can see here in the rating unit list, there's also that family. In this case, they both point to the same thing, that count category, which drives the recommendations, essentially the list of what transformations are logical to use. So another good point, another good reason to make sure when you're describing your assessment that you're picking from the list. Because here's a real good example where ARM can be even smarter for you and more helpful if you've picked from the list, because now it can know and recognize and understand what type of data we're dealing with in order to give us the best possible outcome, best possible selection here. All right, while we're here on the recommendations, we can go even further on this proposed square root transformation if we'd like to understand even more about what we're getting ourselves into here by running this. So there is this little graphs tool here. And what I'm going to do, I'm going to do a 2x2 layout. I think it's a little easier to see. And then when I click on this show, ARM is going to generate for us a few diagnostic graphs that center around the selection I've made. So here I've clicked into this AS row, And so you can see the designation here. It's going to draw a graph to help us visualize this proposed action of the square root transformation. So when I do that, we actually have a PDF that just opened up. And just to show real quick, there are 2 pages, a bunch of different graphs. So page 1 here, what we're looking at on the left, we have graphs that represent the AOV residuals. So really kind of matches the IID column, if you will, from that table from before. And we're drawing a variety of graphs to look at the data before we've done any action. So we get a box whisker, which helps us to visualize the Levene's test. So we're looking at, the height of the boxes, tells us just how variable the residuals for each of our treatments are. But we can see, treatment 1 has a lot of variability in its residuals, whereas treatment 2 is pretty small, and really the rest of them are mostly small. And I think that's the trigger there. We can see our p-value that indeed we are failing that test. There's a few other plots, the normal QQ plot, that helps us with the normality and kind of matches up with our Shapiro-Wilk test. So just looking at the plot there, all the different data points. If I move down to the second page, there's a spread location to give us a sense of skewness. And then finally, there's a histogram to give us, a visualization on how kurtotic the data might be. So that's the first column. Let me go back to the first page. The second column, if you will, is the proposed transformation. So in this case, if we apply the square root transformation, now let's draw these same graphs and visualize our results. So this is what the residuals will look like after we've done the square root transformation on every data point. And we can see our p-value as well. You can say, hey, we have achieved homogeneity of variance. They're closer to each other than they were before. And it can be worthwhile to check out these other plots to make sure we haven't introduced a problem with any of these others. They all look pretty good there. So that's the diagnostic graphs, and you can click that button here or up on top in the diagnostics panel, the same idea. Just depends on what one you're clicked into, that'll change what graph type. So real quick before I move on, if I were in like the IID, then when I do that graph, same overall structure, but kind of the before and after is on the left, it's just the raw data points. And then the right is the residuals. So that's the comparison you would get with the IID. Otherwise, most of the other ones you would be graphing the, the proposed correction. And a nice way to visualize a before and after of if we leave it alone versus if we take this action, can we see an improvement on what it is we're hoping to improve. So the graphs, they might be a little overkill for some folks, but if you want to dive deeper, that's kind of an option here. I would say in general, 90% of the time, totally unnecessary. If you want to geek out, if you want to really understand the data, maybe you only do it for 1 or 2 assessments in a trial anyway that you really want to understand. It's easy to generate, but probably a little overkill as well as far as just the overall flow of reviewing data. But I kind of want to make sure to show every function that we have here on the diagnostics. So to tie a bow on column 2 here, we've looked at that. We've investigated the graphs. We updated our basis to make sure ARM knows what type of data we have, and we're feeling very, very good with the square root transformation. What I can do, I can click the little checkbox next to AS up top here, just like I did with the IID, and that will trigger that action, and it'll just put it in the action codes. I can also double click in the recommendations table. Same thing happens. I want to choose this, and it's the very same as if I hand typed the AS action code. And just to show, all this is really is an instruction to ARM later on. So it's an instruction to perform a square root transformation, but only when we're doing the analysis. So you'll notice my raw data has not changed at all. One of the nice things here, we're not changing data, we're not moving anything around, we're not even making a new column. Everything is just self-contained. I've got my data the way it's always been. We're just going to pass along instructions for when we perform the analysis in ARM to do something extra. Real quick, there was a question on calculated columns. So yeah, everything we've done so far has been on raw data, but it most certainly works in the very same way for a calculated column. Let me peek here to see if I have anyone. We do. So eventually we'll get around to one where there is a calculation. And really, I think everything I've said so far would apply the very same to a calculated column for sure. And we'll be able to add on an action code and not change the transformation either. You know, that calculated column, we'll see when we get there. It's not going to change your calculations either on the screen. It'll still be those instructions. The higher level question, should we, I guess the theoretical ideas that we've talked about either before or that we've recapped today a little bit on the assumptions of ANOVA. If you're going to pass along a transformed column, you want to summarize that with ANOVA. I do really think you need to perform this process and looking at the assumptions of ANOVA before you process your data, whether or not it's transformed. Now, you know, if your calculated column is a square root of your raw data, you know, if you create a new column and that just is the square root because that's what you do in the industry. In whatever research I'm doing, everyone always takes these raw counts and we just always do the square root. Then it might be a little different. Then that might be where you have to think, if I'm already creating the second column because we're going to address up front the fact that we know the distribution of this type of assessment is never matching our AOV assumptions, so everyone always does the square root, then that might be the one case I can think of where maybe you don't need to check everything. I think I still would check it, but then it is just a matter of another layer of thought process when you're looking at a transformed column, you know, that you've already been planning to consider the assumptions. Yeah, you kind of have to think long and hard at the results. If you are seeing an issue, what do we do? And at that point, probably that would be the time to bring in a statistician. I'll admit I'm not a statistician. We do have one on staff, Peter Clausen. If you've ever gotten emails from him or worked with him, he's excellent. He knows way more than I do, and I just listen to him and try tried to pick off as much as I can from him, but it's a perfect example where I think the process I'm describing here is like a 99% of the time that, this is the way to do it and it'll work great. But I think there are some good cases where, hey, it's not as simple as that now, is it? We've got these other calculations or things like that. Another example would be tab, TIO. So that would be like your Abbott's calculation or the incidence. Am I remembering right? Your Abbott's would be a percent of check, percent of control. I think that one would be valid. I think that would be a pretty common. Well, I'd have to think about that one. Depends on which Abbott's you're running. The one where you get the same answer for every replicate in a treatment, then it is irrelevant. There's really no statistics that you can run from that. So it would be irrelevant to do these assumptions. Percent incidence, the TIO, I think so. I think you would want to do this process as well. Again, really the short question is this data, whether it's calculated from other data I took or if it's the raw data itself, is this data something I want to analyze with ANOVA? And if it is, I think 99% chance you want to do this process because if you have these assumptions not being met, you really can't trust the results. And the problem is, this is a computer program, and you tell the computer program to run an analysis, it's going to do it. It's going to give you an answer because you told it to do it. Even though, hey, if you haven't reviewed the data, you might not be able to believe anything that analysis says. But the computer is going to do it because you told it to. So that's the big overall message I kind of try to hammer home with the data review in general. Is let's make sure to do this process instead of just blindly taking whatever answer the software gives us. Great questions, and there's one more here too, tying in with our data confirmation discussion and outliers. So we spent a lot of time trying to find outliers, extreme values, high or low, in your data. But yeah, I really pushed people to not just throw them out. Oh, this is an extreme value, throw it away. Let's think about whether we should or not. That definitely is going to play a role in what we see here. So I agree 100%. If we've kept those outliers, those extreme values, that very well can have an effect on what we see here. So question being, if ARM is looking at outliers for the distribution evaluation, I guess in some regards, this p-value here, this running the Levines, it isn't like looking for outliers. ARM is not performing any outlier calculation and excluding anything. It's going to take everything that we've chosen to include and package that together. So back here with column 2, actually, if I were to draw the heat map, you can tell there's a couple big values. That 165 really called out to me. So there are a couple of extreme values here in this data set, that column 2. And I would say that is very likely contributing to our Levines failing. And that would make sense. Those extreme values are making those treatments more variable than the rest of them. And thus, we're tripping on this requirement for homogeneity of variance. So I would say those outliers definitely are playing a role. And that's kind of why I have it as a separate step. Our first step was to look at these data points that are extreme and decide, number one, find them. Hey, we see them. Now let's think, are they realistic or not? Should we throw them away because they're wrong, or maybe they are actually what occurred and we need to include them in our analysis, as messy as it makes it? And so we've chosen to keep them in, and all we're really doing then is bringing that square root. That'll kind of bring down those extreme values a little bit. It just kind of dampens everything with the square root. So those very large values are just not as large as before. It gives us a little bit closer to what we need. So in some ways, no, we're not doing an outlier calculation in this phase, but certainly those extreme values, those outliers, are definitely affecting what our results are, which I think is good. That's really what we should see. Great questions. I like to call back to of our previous session. A couple more questions. I'll just go one by one here. So in the case of no transformations could fix the problem, yes, we will run non-parametric analysis. So we'll see that in just a moment. Great question. So that's confirmation. You've got the right answer. That is what we'll see. Is there some kind of data that should not be transformed? Something like a non-born data weights, for example. I would say that would come down to you, the researcher. I believe it's really less about the data. This type of data shouldn't get a transformation. It'd be more about, is this data that we've collected something that we are going to analyze? And certainly there might be assessments that you take that tell you some information, but you don't need statistics. We're not trying to summarize that data. And so I think that would be an example that you wouldn't need to transform. You wouldn't need to do this whole process if the assessment itself isn't one that we want to summarize. And that ties in, we do have some action codes like the NM that we showed last time that could be marked even from the very beginning when you first fill in that assessment. Throw in the NM to tell ARM, do not analyze data. This data, we need to collect this data. Oops. We need to collect it, but we don't need to summarize it. And then that's a good way to point out what doesn't need a transformation. I don't need to waste my time on this. There's NM right here. I don't even need a review. I can move on to the next column. And the last question is also AR. So we'll keep moving on kind of quickly here to get to that AR example. Great questions, great discussion. Thanks for that. Yeah, we've covered almost every scenario other than the AR. What I do want to show, so it takes me forever. It takes a full half hour to just show this process. But I do then really like to point out, it doesn't take a half hour for every assessment column for an ARM user to do this review. It can seem daunting, and in training, we have to talk through everything and through the whole idea process. So I really like at this point to just state the fact that it actually is pretty fast to use this tool. So I'm going to go through a bunch of columns. It's a lot faster than it is when we're training. So column 3, what I do, if I'm sitting here and reviewing all these columns, I usually don't even look at this table. My eyes go right to the recommendations list and right into the code, 1, 2, 3, 4. If they all say IID, I know I'm good. There's nothing that has to happen. I'll just double click on any one of these rows and we're good. IID is there. I can move to the next column really fast. Now this one I see I have a code, so I do slow down a little bit. Okay, now I got to think a little bit. Levine's transformation. My next thought is, let me look at my basis. Okay, same thing as before. So the rating unit or the rating type, ARM is learning something. So I feel pretty good about that AS. Again, if I want to really think about this, because this column is super, super important to me, if it's the yield, whatever that really big assessment that I'm going to make a graph on later, maybe I would look at the graphs and try to understand the data. But we've been doing this disease count over and over again. So I'm content, and it's kind of the same thing that happened before. I'm content taking AS and just moving to the next column. For IIDs, fast and easy. Another one. So you can really go pretty quick. Of course, it's going to depend on your research. If all of your assessments are running into assumption problems, then it might take a little more time, but you'll probably still in either case kind of get used to that pattern, like we saw with the count data, that oh well, it's AS a lot. Once you do it once, it's real easy. So I'm just cruising through. Here's my calculated column. This was that AUDPC. Still the same thing, really the same idea. In this case, I don't have any actions extra to do. When I click on the IID, I just want to point out all the existing codes are still there. So the calculation is completely untouched, and we've just tacked on one more piece of information. So no harm, no foul for a calculated column. All right, now we're at the good one. Column 12. Here I've got a lodging assessment, and we have a mess in the table up here. I'll switch my basis back to assessment values just to show that AL, AS, AA, no matter what data correction we do, we just cannot get the normality right. Okay? Between the Spear-Wilks, skewness, kurtosis, almost everything is almost always failing. So we don't have our option for a data correction. None of them fix that problem. Back on our slide, we really had three choices. So another option would be to consider a spatial model. And to do that, you just turn on this checkbox at the top, and you'll see this table gets a lot bigger. We've added a bunch more. It's just different options ARM can consider. And so these are the different analysis. This would be a trend analysis of N and T. It would be a trend analysis, I think linear, quadratic, and then these other ones are nearest neighbor. I don't know why it keeps displaying that way. Nearest column neighbor, nearest row neighbor, nearest row column neighbor, all the different combinations of spatial models that can be run. And then there's some numbers here that are added, the AIC, BIC, those are just model selections. So just trying to decide between all these different options, which model maybe maps things the best. I'm definitely not an expert on the spatial models, but that's kind of the bare minimum there. Luckily for us, ARM, we can still use our recommendations table. So the same idea. If you're not quite sure all of those calculations and what they all mean, we do simplify it here on the recommendations table. According to the AIC, it's recommending the NCN, and actually both of these model selection criteria, both of them point to the NCN, nearest column neighbor, I believe. So that would be the recommendation if you want to use a spatial model. The key is, if you are using a spatial model, you are throwing out your blocking. So we're kind of just tossing out RCB design, that blocking we did, and we're kind of starting from scratch based on the numbers there in the spatial model. So that's one item in our toolbox. If I turn that off, though, the third option, real quick to the question, AA is the automatic arc sine square root %. So that's just one, another data correction transformation we can do, just like the square root and the log. And then this AR stands for automatic rank. And the rank transformation is actually just really running non-parametric statistics. So this is our kind of our final option. In this case, everything failed, all of our data transformations fail. What we can do instead, and we see that recommendation here under Shapiro-Wilks, is because our transformations do not improve normality, what we can do is just throw out ANOVA entirely and let's run a non-parametric statistics instead. And so those tests are a little less powerful. So that's why in general, everyone runs ANOVA if they can, but they're certainly valid and they work just fine. It's all based on ranks. So you take all of the data points and you rank them highest to lowest, and then you actually can still calculate a mean. It would just be the mean of the ranks for each treatment. And that's real handy for us because then those means we could use to run a mean comparison test. And so we'll get to use this column in the same AOV report. There just won't be the AOV analysis that's run on this particular column. It'll be the non-parametric statistics instead. So that's the AR here is going to run the non-parametric statistics on column 12. Column 13, same issue. We never fix, in this case, the Levines. So I'm going to need the AR. And I don't remember how many more columns we have. We're almost there. 14 looks like kind of the same deal. Moisture, so we probably won't care that much to analyze it, but that's fine. And last but not least is our yield. No problems. So that's the process. Just to kind of put a bow on that AR quick, I am going to generate an ANOVA report. Let's just drop these two off. The AOV means table. Just checking quick any extreme options that I have by default. Doesn't look like it. Okay. Just to show that non-parametric statistics, what it looks like on your report. It's nice in the fact that we don't have to do something special. We don't have to generate a totally separate report for the columns where we have to do non-parametric stats or anything like that. It fits in real nice with our typical AOV report. And we'll go into more detail next week about what this report is, some of the options. So I'm just going to go really quick. But going through 1 through 4, 5 through 8, I just want to find column 12 was that first one where we had an AR. So you'll see in general, just at a first glance, nothing particularly special happened. We have a column, we've got treatment means, we've got our mean separation test, and we've got statistics. Of course, it is a little different. And the key here, there's an R footnote on our LSD. And I guess there really isn't anything else that really stands out. But if we look at our footnotes, and I'll zoom in a little more so we can see that what R says is that mean comparisons are based on plot ranks. So we're still able to perform, in this case, we perform an LSD mean comparison test on the ranks of the data in this column. But we still have that mean comparison test. So we do have letters as a result, and we show the means here. Depending on your options, you can either see the rank means, but usually that doesn't mean anything. So most commonly, we'll display the raw treatment means on the report. So that's the non-parametric statistics. Behind the scenes, something happened different in this column compared to the rest of these, but reporting wise, it takes care of itself, which is nice. There is a question about transformed columns and only seeing the transformed values. I think we'll probably be able to spend more time on that next week, but it would tie in to on your general summary. About halfway down, there's a couple options related to transformations. And the key would be whether you want to de-transform your means or not. So I'm guessing from the way your question is phrased, I'm guessing this option is off right now. And so you would see square root, if you had the square root, you'd see a bunch of tiny values. They're really small because it's showing you only the transformed values and their means. If you turn this on, ARM can do the inverse transformation, you basically square those means again, so that way they're back in the usual format, your usual size and units. So I think that's probably what you would want there in that scenario. Real quick, I have one more minute just to show the last option on this panel. There is a button to save to R or SAS. So all of the code that performs this analysis can be generated and you can use it, whether in R or RStudio or the equivalent code in SAS. You can just generate that by choosing an option and it'll spit out the appropriate file type that you can save anywhere. If you want to just see what we're doing, kind of understand better, or if you want to piggyback on that code and run your own stats or analysis from that, feel free to go ahead. That's just at the bottom here. And one more thing, in the print reports, you may be used to seeing questions where ARM is offering to perform a transformation or a treatment exclusion. That's kind of the old system. So there's a whole set of tools we had 10, 15 years ago when they were first added. Those are all tied to just the raw data calculations. And then we added this column diagnostics process, and that's more modern statistical routines that we've included there. So if you're used to that old way and you kind of want to move to this new way with the diagnostics, in the AOV mean stable reports, under the general summary tab, you can turn off those old questions here at the bottom. This really long option, apply automatic transformations or treatment exclusions to data columns that violate assumptions of AOV. And by default, it would be set to prompt, and then ARM will ask you, do you want to do these things? Once you switch over to the diagnostics, you can set that to no. And really, like I said, it's just more modern statistical routines. Also, we don't recommend treatment exclusions anymore because that's kind of a pain to throw out an entire treatment just because the assumptions don't fit. So that's kind of a natural upgrade, if you will, turning off those old routines and functions and use diagnostics for each column. If we have time, we might go over that in a little more detail next week in the reporting, if I went through that a little fast. All right, well, as usual, we got a little long-winded, but we did have some real great questions and discussion throughout, so I really appreciate that. Hopefully we'll be seeing a lot of you again next week when we wrap up this series on reporting. We'll talk analysis. We'll do some more of this type of thing, talking about the analysis and different options that we can turn on and off and when you might want to do that. So thanks, everybody, and hopefully we'll see you next week.
Thank you, Matthew.
Thank you.
Thank you. Very useful session.
Thank you.